In the next few minutes or so, I'm going to discuss 4 identities that is obeyed by the inverse trigonometric function. The first identity is obeyed by the trigonometric function is this one that you see on the screen. Then there are also the second trigonometric function, the third one, and the fourth one. These are all very simple trigonometric identity which can be easily proven or shown using the geometrical argument. The first identity to be shown is that the cos of x, the arc cos of x plus the arc cos of negative x is equals to be a constant. So what constant is that? So let us take a look at this carefully. Say you have on an xy plane, and then you have an angle where the angle has a radius of r equals to 1, and I imagine that this is lying on a circle with the unit radian of r. Then the x coordinate here is describing this point that is given by x and sine theta. Then you imagine that the point is being reflected about the y-axis, so that here you have minus x instead of x. Then you have this point that is reflected about the y-axis. Then this point has a coordinate of minus x, and the height between these 2 points are the same with sine theta. So we would like to look at this trigonometric object a little bit closer. Let us label this angle to be also theta because of the symmetry between this point and this point. They are just reflections about the y-axis, so that x become minus x on the other side. Then you can look at this angle. You can see that this angle is phi. So you can actually write down a very simple relationship between phi and theta. That is, phi is just equals to 180 degree minus theta. So it's a very simple geometrical relationship. 180 degree minus theta will give you phi. And phi here is a number that is less than 90 degree. Once you have written down that, then I'm going to write down 2 relationships that would relate the cos of the angle theta and x. So the first very simple relationship to write down according to the in the forms of an inverse trigonometric function is that the theta is just equals to arc cos of x, and then you write down the phi is okay, let me write down the cos of phi. Cos of phi is according to the definitions of the angle. The phi here is more than 90 degree, and according to the definition of this angle, cos phi is equal to the ratio of the x coordinate divided by the hypotenuse. So this has been mentioned earlier on when we discussed the definition of a trigonometric function in, I think, chapter 1. So according to the chapter 1, I write down the expression of cos phi equals to just the x coordinate of the point here, and also the radius, which is just r. So I have this very simple relationship, and I'm going to translate this relationship into the form of an inverse trigonometric function, which is to say that phi is arc cos of minus x. This is written down by taking the arc cos on the left and arc cos on the right. When I take the arc cos on the left, which is the arc cos of the cos of phi, then I have a phi. Then right hand side is arc cos of minus x. So I have this equation and this equation. I'm going to rewrite this equation again by expressing pi over theta equals to arc cos minus x. So I call this equation number 1, I call this equation number 2. Then from equation number 1 and number 2, then you can easily see that these two would add up to be a constant. So let me show you what I meant by that. So for equation number 1, you have theta equals to arc cos of x, and from the equation number 2, theta is just equals to pi minus arc cos of minus x. So we have then this very simple relationship that is the sum of arc cos of x and arc cos of negative x is a constant of pi. So that is the first identity that relates the arc cos of x to arc cos of negative x. So I have just proven this simple identity. For your information, this identity would not be used a lot. The more relevant identity that we will show to be having some kind of usefulness is the identity that involves the sum of arccos and arcsine, as well as the sum of arctangent, arcotangent, and the sum of arccosecant and cosecant. We're going to show you, for example, how to obtain the relationship between the arccos and arcsine. So again, you construct a right triangle, then you label the angle here as theta, and this is a height of the triangle to be x. Once you have done that, then according to this relationship, let me write it down here and reconstruct it again. You label this to be a theta, it's 90 degree. Then you say cos theta, which is the ratio of the adjacent and r to be x. That would mean that this is x and r is equal to 1. So you have this very simple relationship that relates x and r. Then you write cos of x equals to theta. This relationship is written down by referring to the triangle I have just constructed, which is this one. Once you have done that, then you can try to take the angle here. This angle, by definition, is I call 90 degree minus theta. So I think there is an error here. It should be theta instead of phi. So you have to then take the sine of this angle. This angle, when you take the sine, you get also x. So sine of this angle is x. Then when you rewrite this into the terms of arcsine, then you say sine of x is just equal to pi over 2 minus theta. So you have this relationship of x and theta in terms of arcsine, and you have this very simple relationship between arc cos and theta. You join them together, like what I did in the previous slide, then you will find very easily that the sum of arcsine and arc cos is simply equal to 90 degrees. Therefore, you can prove this identity very easily, that is arc cos of x plus arc cos of sine is just 90 degrees by using this kind of triangle, right triangle construction. The next two identity are very similar. You have arc cos of tangent plus arc cos of arctangent, sum of arcotangent and arcotangent. So let me say it again. So these are the other two identity, that is arc cos and arctangent, sum up to 90, arc cosecant and arc secant, sum up to be 90 degree. So these are the identities that relate the trigonometric function, which is very easy to remember. They are just related to each other by an constant. Now later on, we will show that these three identities could help us to simplify the derivations of derivative involving the inverse trigonometric function. The next thing I want to discuss is example 4, which is calculating the angle. Well, not angle. You are given the angle in terms of arc sine of 2 or 3, and you're asked to find cos, tangent, secant, and cosecant alpha. So let us try to do this here in a very quickly manner. I have alpha equals to arc sine of 2 over 3. Arc sine of 2 over 3 is an angle. So I'll label the angle by using alpha. Conventionally, we will label the alpha using Greek alphabet such as alpha, beta, gamma. Then we reserve the symbol of XYZ to real number, which describe non-angle. So when you see an Greek symbol such as alpha, beta, and gamma, that usually refers to angle. Now, once I have written down this one, I ask myself what I am going to answer. The answer that I'm seeking for is what is the values of cotangent alpha, tangent alpha, and let me refer to the notes again. So we ask for find cos, tangent, etc. So basically, all the other trigonometric function of alpha is what we are looking for. So you are asked to find this, and probably you are going to find, say, cos alpha, cotangent alpha, what else? And then secant alpha. You don't really need to find sine alpha because sine alpha is just 2, 3. Okay. So how do you find all these trigonometric functions of alpha? You just first perform an calculation of this trigonometric function, the inverse trigonometric function into the right triangle. You construct a right triangle. Then from here, you understand that sine of alpha should be equal to 3. These two are the same statement. This is a statement in terms of the inverse trigonometric function. This is the equivalent statements in terms of the trigonometric function. So by referring to the trigonometric function, you label the angle here and then you label this is 2 and 3 because the definitions of sine function is opposite to the hypotenuse. Once you have labeled that, then the side or this is the adjacent would be then equals to 9 minus 4 square root, which is square root of 5. So now you have successfully translated this inverse trigonometric value into a triangle. Then based on this triangle, you can answer all these questions one by one by referring to the definitions of the trigonometric function. For example, cotangent of alpha by definitions is defined to be the ratio of the adjacent to the opposite. So it should be then square root of 5 divided by 2. That is the definition of cotangent. Tangent is defined to be the ratio of the opposite divided by the adjacent. So that is the definition of tangent alpha. Therefore, we can then obtain the expression of cotangent and tangent. How about cos of alpha is then just the adjacent to alpha, which is square of 5 over hypotenuse. Then once you have done that, you can easily write down secant. Secant of alpha by definition is 1 over cos of alpha, which is then square root of 5 over 3. Then you can also answer the questions of what else? There's no more, right? So tangent, cos, secant. Then you may look at sine alpha. Sine alpha do not need to be calculated. It's just equal to 2 or 3, which could be written down from the expressions of the alpha. So that is the example of evaluating the values of alpha angle from the inverse trigonometric function. So we finish that, then we go to example 5. Find the secant of arctangent of x over 3. So let me write down questions. Secant of arctangent x over 3, yeah. Secant of arctangent x over 3. So this is the trigonometric function of secant, where the arguments of the secant should be at angle. Arctangent x over 3 is an angle. Therefore, we invent a symbol to represent the angle that is in the argument of the secant function. So I'll call this alpha as arctangent of x over 3. Here, x is the variable that is not angle, that goes into the inverse of tangent function. So given any values of x, then arctangent of x over 3 define an angle. You are asked to find what is the secant of the angle, which is alpha. So this is the same as calculating the secant of alpha. So the first thing you do is, again, like what we have done in the previous slide, translate this very simple inverse trigonometric function into an right angle. That statement is the same as saying tangent alpha is x over 3. By definitions, the tangent of alpha is the ratio of opposite divided by the adjacent. So the opposite here is x, adjacent should be 3. Once you have written down that, then you can label the hypotenuse to be 9 minus x squared in a square root. So once you have labeled all this, then secant of alpha becomes very easy to obtain. Secant alpha, by definition, is just equal to 1 over cos of alpha. Secant alpha is 1 over cos of alpha, and the cos is by definition equals to the ratio of the adjacent over the hypotenuse. So this is the expression of the secant of alpha. So the answer to these questions would be that secant of alpha is square root of 9 minus x squared. So I think I made a mistake again here. The hypotenuse should not be 9 minus x squared. It should be 9 plus x squared. Hypotenuse is the square of the adjacent plus the square of the opposite. So this is the hypotenuse, 9 plus x squared in the square root. So that is the expressions of my secant alpha. It would be square root of 9 plus x squared over 3. Yeah, so that finished the illustrations of an example 5. To do these questions, what you have to do is basically to understand that you should translate the inverse tangent function into the form of an right triangle. Then you label the triangle properly, specifically label the angle alpha and the opposite and adjacent based on the definitions of tangent alpha, then you can solve these questions quite straightforwardly. So you find that you need to understand the definitions of the trigonometric function very well in order to do these questions. We go to the next bit. Here we are going to talk about the derivative of the trigonometric function. There is a total of 6 derivatives of the trigonometric function, namely the derivative of arcsine, derivative of arctangent, derivative of arcsecant, and also the other 3 derivatives. However, we are going to show you in this exercise how to obtain only the derivative of arcsine, the derivative of arcsecant, and the derivative of arctangent. So once you have obtained the derivative of arcsine, arcsecant, and arctangent, the derivative of, say, for example, arccosine, the derivative of arccosecant, and the derivative of arccotangent could then be easily obtained by using the identity that relates the arcsine arccos, cosecant arc, secant arc, and cotangent arc, tangent arc. Namely, we have mentioned earlier on, the two are related by the simple identity of this arcsecant and arccosecant, arctangent, arcotangent. They all sum up to be 90 degrees. So using these very simple identities, you can derive the derivative of this by knowing the derivative of these 3 inverse trigonometric functions. So let us see how you can first derive the derivative of arcsecant. No, not arcsecant, arcsecant. It's not arcsecant, arc of sine. So how do you calculate the derivative of the arcsine? The derivative of arcsine can be easily calculated by using the formula that relates the function and the inverse of the function. Remember, we have these situations. If you have a function and you know its derivative, then the derivative of the inverse of the function could be expressed in the form of the derivative of the function. Evaluate the x at the expression of the inverse of the function. So you can easily calculate the derivative of the arcsine by knowing the derivative of the sine function. So let's see how we do that. Here we would say the function f(x) is the sine function, then the arcsine is the inverse function. So the derivative of the arcsine is just 1 over derivative of the sine function, where you replace the argument in the derivative of the sine function by the expressions of the arcsine, which is just equals to arcsine. So by using this very simple formula, you can then arrive at the fact that ddx of sine x is the cos x. So this cos x is the derivative of the sine function. Then you replace the x by the expressions of arcsine. Then you will arrive at this very simple relationship that you have cos of sine of x. So we will call this say as alpha. Then the next thing we want to do is to figure out what is the expression of 1 over cos of alpha. In order to do that, we always translate this relationship that involve the inverse sine into the form of an right triangle. This is a very simple tricks. So you label the alpha, then sine alpha equals to x is then translated into labeling the opposite as x and the hypotenuse as 1. So that is the labeling of translation of arc sine of x equals to alpha into the right triangle. Once you have done that, then what we are looking for is an expression of cos alpha. So from here, you can easily obtain the cos alpha to be the ratio of the adjacent to the hypotenuse. The adjacent to the alpha is the value of 1 minus x squared in the square root. So cos alpha is 1 minus x squared over the hypotenuse, which is 1. So we are almost there. Here you get this to be 1 over square root of 1 minus x squared. So that is the solutions to the d dx of the arc sine of x. That is how the derivative of the arc sine is calculated. Then we try to generalize this derivative to the case where x is promoted to the function of x. Here, the d dx of arc sine of the function u is to be calculated. And what is this? This is just equals to the d dx of u and then d arc sine of u over du. Here I am applying the chain rule where the arc sine of u is to be treated as an composite function of u. So d dx of an arc sine of a general function u is then the product of du dx times the d du of arc sine of u. Then this can be written down quite straightforwardly to be the product of du dx times the d du of arc sine of u. Here, this d du of arc sine of u can be just written down. If you know d dx of arc sine. So here you have a d dx of x. Here you have x. Therefore, d du of arc sine of u is simply replacing the x by u in the expressions that is derived earlier on. So that is the generalizations of the differentiations of an function u in the arc sine. In the very special case where u is just simply equals to x, then this relationship here is then reduced to this very simple relationship. So we have now finished expressing the derivative of arc sine of u. That is the result that is shown in this slide. Slide I mentioned is this one. So we have finished doing that. The next thing I want to show you is to perform one more generalizations to make u to become dependent on a. And we need this relationship for later when we were to apply this relationship to obtain the integration. But maybe let me try to derive the integration version from this very simple relationship instead of calculating the derivative of arc sine of u over a. Okay, so from this very simple derivative relationship, then we can proceed by calculating the indefinite integrations of these equations. That is what I'm going to do. I'm going to put or create an indefinite integral symbol, then slot in this into here and slot this into here. So this is a shortcut that allows me to obtain the integration version of this differentiation function. So if I do that, then I get dx of arcsine of u. Here I should integrate with respect to x instead of dt. So I'm sorry. So I mentioned like I sometimes is being inconsistent in my writing and my speech. Okay, so I have then slot in the expression of ddx of arcsine of u into the left hand side indefinite integration. Then I'm going to slot this in into here, and what I get is 1 over u squared du dx. So let me make some slight simplification to this equation. On the right hand side, here I have du dx and this is dx. So the product of du dx and dx is nothing but just the differential of du. So I have this relationship 1 minus u squared in the integration. And then I'm looking at the right hand side here. What is d dx of arcsine of dx? So this could be understood to be an process of taking the differentiation and then integrate it again. Right. So let me explain what I meant by that. So initially you have a function, you have a u, then the u is being taken to the arcsine. Okay, so let me write this again. So imagine that initially you have an function called arcsine of u. Then this object is being differentiated by an operation. So after the operation of taking the differentiation, arcsine of u is brought to the ddx of arcsine of u. Then what you do is that you perform an inverse operations of the ddx, which is the integration. So you take the indefinite integrations that would then brings this expression back to sine u. So this process is just this, okay? So this is a process where you take ddx of arcsine of u, slot it into the indefinite integrations. So finally, you end up to be the sine. So by understanding this to be an cyclic operations of going from sine arcsine of u to ddx of arcsine of u and then integrate it back to arcsine of u, then this whole thing is nothing but just the arcsine of u. And again, if you remember our definitions, the indefinite integration sign is representing the collections of all antiderivative. Therefore, whatever come out from this indefinite integration, you have to slot in with an constant. So that is the results that we obtain. Namely, if you have a function in the form of 1 over 1 minus u squared du, then what you get is an arcsine of u. So this is an indefinite integrations that relates the integral of 1 over u squared and its antiderivative, which is arcsine of u. So when you integrate 1 over square root of 1 minus u squared, then the result will be the arcsine of u. So this is basically the results that is going to be shown in the next part of the slide. Let me try to find you where is this. So this is basically this relationship number 1. However, for this number 1, it's not in terms of 1 minus u squared, but it is a squared minus u squared. So this result that is shown in table 7.4 is a slightly generalized version than the result that I show you here. If you make u to become u over a, then you'll get a result that would read like square root of a squared minus u squared equals to arc sine of u over a plus c. You would be able to show this. You're able to show this from this relationship by replacing u by u over a. So that is the integration formula that involve 1 over square root of a squared minus u squared. But here the condition is that the a squared minus u squared must be an positive number. Okay, so that is the derivations of the formula 7.41 that is obtained from the differentiation that involve the argument of arc sine. Now, there's one more thing I have not shown you. I have actually not shown you exactly how to go from this formula, to this formula. So you can try to figure out how to do this yourself. It's actually not that difficult. Let's see if I can do it easily in this case. So maybe I would try to do this here. Let's try this. Okay, so I'm going to show you how this formula can be obtained. So I'm looking at the situations of the derivative of this. So let me look at this formula again. d dx of arc sine of x is 1 over square root of 1 over x. So I'm going to show you that arc sine of x over a. How do you calculate the d dx of arc sine of a, given that you know this knowledge? Now, once we have obtained the answer to the d dx of arc sine of x over a, then you can then generalize this to arc sine of u over a. Then you perform the definite integrations. Then you'll be able to arrive at the formula that I mentioned earlier on to you, namely the equation number 1 in table 7.4. So now we are trying to derive these relationships. We begin by asking the question of what is the derivative of arc sine of x over a. So to do this, we can simply say use a very simple replacement, say q equals to x over a. So you make this very simple substitution. Then from here, you get dq dx, which is just 1 over a. So now with this, you would then perform the differentiation of this function, d dx of arc sine of x over a, which is q. You perform the differentiations of arc sine of q with respect to x by using the chain rule, d du of arc sine of q, not u. So here this is the x, d dx of dq, then you have dq dx. This is the applications of the chain rule. Then what I have is d dq of arc sine of q. The d dq of arc sine of q is nothing but just 1 over square root of 1 minus q squared, which I easily write down because I know what is d dx of arc sine of x, right? So d dx of arc sine of x gives you this, therefore d dq of arc sine of q will give you this. Then you have dq dx, which is then 1 over a. So the 1 over a is obtained from this very simple expression. So when you do some simple algebra, then you have q is x over a, so you have a squared minus x squared, and then you have a squared here, you have an a outside 1 over a. So after the simplifications, you find this equals to square root of a squared minus x squared. Okay, so I think that should be correct. Now, if this is correct, then what I have arrived is d dx of arcsine of q, where q is just x over a. Right, so this is the definition of q. So I just replace the x by x over a in q. Then I arrive at this expression, which is 1 over square root of a squared minus x squared. So that is the relationship that could be then easily generalized by replacing x with a general function of u. So when I promote these relationships for x into a full function, then I can do that by using the chain rule again. D dx of arcsine of u over a is then d dq d du of arcsine of u over, let me see it again, d dx of sine of u over a, where I just replace the u by the x by u. Then I apply the chain rule, which is d du of arcsine of u over a times du dx. So d du of u over a is just the same as this. Okay, here I have x over a, here I have u over a, here I have x, here I have x, here I have u, I have u. Therefore, this expression d du of arcsine of u over a can be obtained from this expression, where I simply replace the x by u. Therefore, I have arrived at this expression of 1 over a squared minus u squared du dx. So once I have done that, then I would take the indefinite integration with respect to x on both sides. So I'll fill up this with this. I'll fill up this into, I'll fill up this into here. So I then would be able to arrive at the fact that d dx of arcsine of u over a dx on the left, then right hand side is 1 over square root of a squared minus u squared. Here is the product of du dx and dx, and this is du. So finally, I'll obtain this one. So I write this on the left. That is the integrations of a squared minus u squared with respect to u is just equals to this expression on the right hand side, which is basically then arcsine of u over a plus n constant. So that is how I prove these equations. That tells me if I have a function of u and integrate it in this manner, then the right hand side is arcsine of u over a, which is just the equation number 1 that is seen in table 7.4. That is how I arrived at these relationships in number 1 of equations of table 7.4. So it seems a bit lengthy in the derivation. However, if you follow the argument throughout, you find that you can actually derive all these relationships quite simply. That is, you can easily obtain the derivative of arcsine. Then from here, you can generalize the x to u. Then from here, you perform the integrations, you'll be able to obtain the result of the integration that is shown here step by step. All these steps requires you to have a good idea of all the knowledge that we have already discussed in all the previous lecture. So I have just shown you the calculations and the derivations of the function involving only trigonometric, involve the inverse trigonometry of sine x. So basically, you can apply the similar techniques to other trigonometry, other inverse trigonometry function as well. Okay, so up to this point, I have shown you how to obtain the derivative and the integration involving arcsine. Then these are the example 7 that shows you how to take the derivative of arcsine of x squared. You just apply the chain rule where you call x squared by u. So this is the same as the du of arcsine of u times du dx. This is chain rule that could be applied. So du of arcsine of u has already been calculated earlier on, is just this result. So du dx is just equals to 2x. So finally, we have 2x over 1 minus u squared in the square root, where u squared is x power 4. So that is the result of this. In case I do not make any error, it will be the answer. So we have finished example 7. The derivative of arctangent could be easily derived yourself by looking at the slide. So I would not go through the derivations of arctangent rigorously. It should be easily obtained if you go through these slides yourself. So the same thing would happen as well by promoting the x into the u using the chain rule. Then you derive this result from this result, where the difference is just that here you have a u instead of just an x, where u is treated as a function of x. Then you can try to do these very simple questions by setting u as square root of t. Then you can take x as a function of u. Then you would calculate dx dt using the chain rule. Dx du is the derivative of x with respect to u, which is just d dx. So which is just d du of arctangent of u. Then you have this du dx. So from here du dt, not du dt, not du dx. So here this is du dt. Is just t minus half with a factor of 2. That is a factor of half. Yeah. So anyway, I think I might be doing this correctly, hopefully. So this will be just 1 over 2 times square root of 2. So this du of arctangent of 1 over u is just 1 over 1 plus u squared. Here you have 2 square of t, where you just replace the u squared by t. Then you have a square of t, you have a 2, where I have made use of the fact that d du of arctangent of u is 1 over u squared. So this is the result that is obtained from this very simple rule. So that finished the example 8. Okay, so this is a derivative of arcsecant, derivative of the arcsecant of u over a, example 5, and also the other formula. You can try to understand the derivations of arctangent, the derivations of arcsecant yourself, the derivations of the other inverse trigonometric function to be obtained from this identity. So this is a summary of the derivative of all the 6 inverse trigonometric functions. This is the example 10. You just need to calculate the derivative of the function arccotangent at x equals to 1 to slot in the values. Then you calculate the formula for it. Please read this yourself. We are not going to discuss this here. And then the integration formula, as I mentioned, has been derived for 7.4 equation number 1. If you know how to do this, you should be able to know how these two formula is derived. And these are the example using the integration formula. So I'll let you to run through this all by yourself. The formula for the integration and differentiation are actually provided to you in the exam sheets, right? So you should refer to the formula sheet that you will get in exam. These are the formula that let you know how to calculate the differentiations of the inverse trigonometric function. So you don't really need to memorize this. You can just take over from the formula sheets, but it will be best if you can know how to derive them yourself.